All right, question number 31, true, false. It wants to know which one of the following is true. A says cesium has 82 protons. That's not true. It has 55 protons. B says nuclides with larger binding energies are more stable than those with smaller binding energies, and that actually is true, which means we could probably skip and keep going, but I'll address the other ones now anyway. Beta emission occurs when an electron is converted into a neutron plus a proton. That is not true. Beta emission is when you get a neutron that becomes a proton plus a beta particle. D says an alpha particle is the antiparticle of the helium atom. That's not true. The alpha particle is the helium nucleus. Okay, and alpha is a helium nucleus just like that. E, nuclear fission involves the combination of lighter nuclei to form a heavier one. That's also false. Fusion is that process. Question 32 says, determine the identity of the daughter nuclide from the electron capture of aluminum 26. So we would write this out like so, aluminum 1326. And this is going to capture an electron. So we're going to be adding to this an electron which has a mass number of 0 and -1. And what we need to do is write something on the other side which balances both the top numbers and the bottom numbers. So the top numbers on the left, 26 and 0, add up to 26. And the bottom numbers, 13 and -1, add up to 12. Element number 12 on the periodic table, if you look that one up, is magnesium. And so that should be our answer for this question. In the following equation, what particle or type of radiation needs to be included on the right-hand side in order to balance it? So here we have indium 108 going to cadmium 108. And what else is produced? Well, we know whatever it is that's produced must have a mass number of 0 because the sum of the mass numbers on the left and the sum of the mass numbers on the right have to be equal. And we already have 108 on both sides. And then if you look on the bottom, we have a 49 on the left and a 48 on the right, so we need it to be +1 on the bottom in order for the right-hand side sum to be equal to the left-hand side sum. So what kind of particle has 0 mass number and +1? That is a beta, which we also call a beta plus or a positron. Question 34, identify the nuclide that completes the following nuclear reaction. Okay, so again, we want to balance the top numbers and the bottom numbers, so whatever fits in there has to add to 4 to give you 147, which means it's going to be 143 up top. The bottom number has to be 60, so that 60 plus 2 is equal to 62 on the left-hand side. And then we find element 60 on the periodic table. And that works out to be neodymium. That's question 34. 35. Determine how much energy is released in kilojoules per mole when thorium-230 decays according to the equation below. All right, so what we want to do here is figure out the mass of everything on the left and the mass of everything on the right, and find the difference, and that difference is the mass defect. And from the mass defect, what we're going to be doing is converting that into energy using E equals mc squared. So the mass on the left for just thorium-230 is given in the question, 230.03313 U. The mass on the right, and just put Mr, is going to be equal to the mass of the helium-4 plus the mass of the radium-226. Both of those are given in the question. 4.00260 U plus 226.025403 U, and that sums up to 230.028003. We're hanging on to a lot of sig figs in this example. So our mass defect, our delta M, is going to be equal to the difference between the mass on the left and the mass on the right, which is 230.03313 subtract 230.028003, and that equals 0.005127 U, which is the same thing actually as 0.005127 grams per mole. So we want to convert this into energy, so we're going to be using E equals M, or delta M, I guess I should say, C squared. And ideally for energy, we would like our mass to be in kilograms, and that's because a joule is a kilogram meter per second squared. So we're going to convert that further to actually what I'm going to do is put it in scientific notation, 5.127 times 10 to the minus 6 kilograms per mole. So we can stick this in down below, 5.127 times 10 to the minus 6 kilograms per mole, multiplied by c squared. C is the speed of light, which is a constant, 2.998 times 10 to the 8 meters per second. That is all squared. And if you punch that in, you get a number of 4.61 times 10 to the 11 kilogram meters squared per second squared per mole. It's kind of a weird unit, I guess. Now, a kilogram meter squared per second squared is a joule, so this is equal to 4.61 times 10 to the 11 joules per mole, which is getting us closer to the answer. It wants the energy in kilojoules per mole, so we have to divide that by 1,000. 4.61 times 10 to the 8 kilojoules per mole. Question 36. What is the binding energy of chlorine-35 in mega electron volts per nucleon? It gives us the mass of Cl35, and it gives us the mass of a neutron and the mass of a proton. So the way we think about this is we look at a chlorine-35, which if we were to write out the whole element, we get chlorine-35 and 17. This means this nucleus is composed of 17 protons and 18 neutrons. So we're going to add up the mass of 17 protons plus 18 neutrons, and we're going to compare that to the actual mass of the nucleus. The difference, again, in this example, is going to be our mass defect. Okay, so the mass of the protons and neutrons is going to be equal to 17 multiplied by the mass of a proton, which is given here, 1.00783 U, plus 18 times the mass of a neutron, 1.00866 U. That equals 35.28899 U. The mass of the Cl35 given in the question is 34.96885 U. So the mass defect is the difference between those two. That will be equal to 35.28899 subtract 34.96885, and that equals 0.32014U. This question asks for the binding energy in mega electron volts per nucleon, and if you go to the first page of your exam and you look at all of the conversion factors and constants and all that stuff, you see one there which is very useful in this case, which is 1U in mass defect is equal to 931.5 mega electron volts. So basically this conversion factor just puts that value 1U into E equals mc squared, does the unit conversions and puts it into mega electron volts for you. So what we can do is convert the value we've calculated here into mega electron volts directly by just saying here that the E is going to be equal to 0.32014U multiplied by 931.5 mega electron volts per 1U. The U's will cancel and you end up with a value of 298.21 mega electron volts. Now don't forget the very last step here, which is it wants it per nucleon, and a nucleon is a proton or a neutron. So chlorine has 35 nucleons. So the energy per nucleon is our total energy, which is 298.21 mega electron volts over 35, which is equal to 8.52 mega electron volts per nucleon. Question 37 asks, what's the bonding molecular orbital that results from the linear combination of two px orbitals? So two px orbitals are going to be orbitals that are side by side. We're going to be bringing two of these px orbitals together and allow these to overlap and form two molecular orbitals, a bonding and an anti-bonding orbital, and this asks us to identify the bonding one. So as you bring those two together, the two orbitals that you're going to make, there's a bonding one that's lower in energy, which has the two top halves sort of overlap with each other to form something like that, and then the two bottom lobes also overlap to form something like that. You will also have an anti-bonding combination resulting from destructive interference, which would look something like that. The one we're looking for is the bonding one below, which is what it's looking for up here, and that looks an awful lot like C in this example. Part B asks us for the label for these molecular orbitals. So this one would be a 1, it's a pi orbital, and U is for the bonding. This one would be 1 pi G with a star, optional. You can put the star, you can not put the star. The parity symbol G and U indicates whether it's a bonding or an anti-bonding orbital anyway. I just wanted to point out that to make an orbital like A, what you would need for something like that are the pz orbitals, because the pz are the ones that would be pointing towards each other, and that's because convention states that the internuclear axis, the line, imaginary line that connects two nuclei that form a bond, is defined as the z-axis. Okay, so you have the z's that would form end-to-end overlap to give you orbitals like A, which is a sigma, and the x, px, and the py meet side by side to give you pi orbitals like C. Question 38 wants the bond order for the O2+ ion. These diagrams that are shown in this question right here are provided for you on the formula sheet for your exam. So you will have these available to answer questions like this. So there's, I guess, two main things we have to do here. One is identify which of these two diagrams is appropriate for the O2 plus ion, and it works out that it's going to be the one on the left. This is used for oxygen, fluorine, and neon, whereas the one on the right is used for boron, carbon, and nitrogen. So we're going to be using the one on the left, and so I'm going to just scratch that one out. We're going to have to count up the correct number of valence electrons in an O2 plus ion. So oxygen itself has 6. We have an O2, so there's 2 oxygens, so there's 6 more. And the plus charge means we have to remove 1 electron. And if you add those numbers up, you get 11. So we have 11 valence electrons to fill into this molecular orbital diagram on the left. We start at the bottom, which is the Aufbau principle. We put 2 electrons in the lowest. Once it's filled, we move up. We put 2 more in the next one, so we're up to 4, 5, 6, 7, 8. So we put 1 electron in each of these 2 degenerate orbitals. Degenerate means same energy, before we pair any of them up. But that only gets us to 8. We need to get to 11, so we get 8. Now we compare them, 9, 10, and our last electron we can put up in one of these orbitals up here. It wants to know the bond order, which is the number of bonding, or electrons in bonding MOs, minus, let's call them bonding electrons, minus the number of anti-bonding electrons over 2. So this one is a bonding orbital, this one is a bonding orbital, and this one is a bonding orbital. This one and this one are anti-bonding orbitals. So we count up the electrons in the bonding ones first. So that gives us 2, 4, 8. And the ones in anti-bonding orbitals are 2, 3. Over 2 equals 2.5. That should be our answer for that question. Hey, Sigma, what happened here? Question 39 says, according to MO theory, which of the following molecules will have the weakest bond? And the weakest bond we find out by determining which of these is going to have the lowest bond order. So we have the 2 MO diagrams again, the one on the left and the one on the right. And if you remember, the one on the right is the one we use if we have nitrogen or carbon or boron, whereas this one is the one we use for oxygen, fluorine, or neon. The only difference is the ordering of these 2 orbitals, so make sure you use the right one. So for nitrogen, we have, I guess, 5 different nitrogen species with differing numbers of electrons. So for A, we have N2. Nitrogen has 5 valence electrons, so 2 nitrogens has 10 valence electrons. N2 minus has 11 valence electrons. N2 2 minus has 2 extra electrons for 12 valence electrons. N2 3 minus has 13 valence electrons. And finally, N2 4 minus has 4 extra electrons for 14 valence electrons. So what we really do here is we start filling up the MO diagram for each of these, calculate the bond order, and then whichever one ends up with the highest bond order is going to be one that has the weakest bond. So let's start with A, with N2, 10 valence electrons. We go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the bond order for this would be all of the electrons that are in bonding orbitals. So that would mean these ones, and these ones are all bonding. So that is a total of 8. We have the remaining 2 that are in anti-bonding orbitals, divided by 2 is equal to 3. So we say N2 has a bond order of 3, or that's what we would predict based on the molecular orbital diagram. For N2 2-, we have 11 valence electrons, so we have to add another electron into this. So we would add it up into the next available orbital, which would be this one. Calculate the bond order here, and we would get, in this case, we still have 8 of the yellow ones that are in bonding orbitals, minus now 3 over 2, and this reduced the bond order a little bit by 2.5. Next, we add a second electron, which would go right here. That means we now have 8 minus 4 electrons in antibonding orbitals over 2 is 2. For 13 valence electrons, we add an additional electron, which would go there in the antibonding orbital. This becomes 8 minus 5 over 2 equals 1.5. And lastly, we add 14. We have one more electron to put in, which goes there. That is 8 minus 6 over 2 equals 1. So A has our highest bond order, so that will have the strongest bond. The one that has the weakest bond would be this one, which would be N2 4- because it has the lowest bond order. Last one, question 40 asks the molecular orbital configuration below 2 sigma g 2 sigma, that's a mistake. That's probably should have a u, 2 sigma u2, 1 pi u4, 3 sigma g2. Applies to which of the following row 2 elements or diatomic molecules? One thing you can actually pick out from this electron configuration right away is that the pi is before the 3 sigma. Because it's before the 3 sigma, that means we're going to be using the MO diagram that looks like this, where you have your this and this, and then next the pi's. This would be the 1 pi u. Then we have the 3 sigma g. This, by the way, is the 2 sigma g, 2 sigma star u. And then up here we would have the 1 pi g, and above that the 3 sigma u. And these ones are antibonding, so you can put a star there if you like. So right away we know that this diagram is the one that goes with boron, carbon, and nitrogen. So we can already rule out F2O2 and neon 2 if it was on the list, but it's not. So what we do now is we look at the number of electrons that are put in here. We have 2 in the 2 sigma g. We have 2 electrons in the 2 sigma u, 4 electrons in the 1 pi u, and 2 electrons in the 3 sigma g. So this is equal to 2, 4, 6, 8, 10 valence electrons. Which one of these 3 has 10 valence electrons? Well, B2 is going to have 6, C2 has 8, N2 has 10. So our answer is E.